Welcome to the webinar series about Allplan Bridge solution. In this webinar series, we will show you how to parametrically model your bridge, how to deal with the structural analysis in Allplan Bridge, how to detail and model the rebar, how to produce the drawings and other necessary documentation for your projects, and how to obtain the final beam bridge model. In this first webinar from series, we will show you how to model the railway bridge with a length of 160 meters and the 4 spans. This bridge will be pre-stressed concrete box girder, which cross-section is shown on the right side of your screen. At the very top of the screen, you can see the geometrical model made in Allplan Bridge, and below it also an analytical model made in Allplan Bridge and derived directly from geometrical model. This bridge will be built by using the span-by-span erection method as a cast-in situ. We will use this example in the whole webinar series in order to demonstrate the complete workflow of Allplan Bridge solution. In this webinar, we will parametrically model the bridge by following the shown steps. We will start with axis definition and then continue with the modeling of the superstructure and follow with the substructure elements modeling as piles and piers. After that, we will model the tendons, define the construction sequence, define the smart placements, and finally transfer the bridge model to Allplan engineering for further detailing and drawing production. So let's start with the first step and define the bridge axis. Before we start with bridge axis definition, we will create a new project in Allplan engineering with the name Railway Bridge, keeping all other settings per default. After the new project is created with a wished name, we will go to the bridge construction role, and under the task area Allplan Bridge, we will choose the icon Create New Allplan Bridge Project, which will automatically open Allplan Bridge and link the projects of Allplan Bridge and Allplan Engineering. There are two possibilities in Allplan Bridge. You can create the bridge axis by importing it from BIM+ in the format of land.xml file, or you can create your own axis manually. We will first start with importing the axis from BIM+ platform. For this, we need to be logged into BIM+, and we can do that directly from Allplan Bridge. After the login is done, we will be able to choose the wished project from BIM+, in which we already previously uploaded the wished land.xml model of our bridge axis. After we chose the project, we will be able to choose the wished axis from the BIM+ project, because in one project you can have several different axes. When we chose the wished axis, it will be imported successfully into Allplan Bridge, and we can see the axis in plan and profile, and also this axis will be available in 3D preview as well. It is of course possible in the later phases of the project to change some elements of the axis in plan and profile together with offsets and height and other elements. Under the options settings, you can check the origin offset of your axis and change it if necessary. In the next step, we will manually create the bridge axis to show you how those steps can be done. Naturally, we will start first with the axis in plan and define the begin point of the axis. Since we want that both axes are positioned very close to each other in this project, we will define the begin coordinates of our first point for the second axis, very similar to the first axis. Then we will define the second element, and this is the straight line with a length of 180 meters, We will continue then with the spiral part with the length of 40 meters, and we will finish with the curve or the arc with the length of 50 meters and radius 100 meters. With this we finish with the plan definition, and now we will switch to the profile, and we will define start and end point of the profile with a height similar to the one we had in the first axis. After the recalculation, you are able to see both axes in 3D window and also both axes in plan view. When we finish with axis definition, we can continue with the superstructure modeling, and in that manner our first step will be the definition of the cross-section for the bridge deck. For this, we need to go to the project navigation tree and with the right mouse click on the cross-section menu, create a new cross-section with a wished name. After that, we will go to the cross-section task area, and by using the function for parallel line definition, define several vertical lines parallel to the main y-axis. And in the same manner, we will define several horizontal lines parallel to the main z axis. After this, we will define the first line by angle, which will define the crossfall of our deck with 2.5%, one line parallel to it, and also two additional angular lines which will define the inclination of the cross-section of our main girder. When we finish with the definition of all necessary parametric lines, we will define the boundary of the cross-section by connecting the corresponding intersection points. As you can see, we define a boundary of the cross-section by starting and finishing with the same point and closing the boundary. When the boundary is defined, we will add some visual improvements to the cross-section. We will use the function round boundary point and add some roundings to several boundary points with the values of 0.3 and 0.15 meters. In the next step, we will define the structural unit of type beam. For this, we need to define the position of the structural unit and to assign the boundary to the structural unit. The position of the structural unit within the cross-section defines the structural node of the element series for the future statical model. All the elements set up as structural units in the cross-sections are used as 3D bodies for modeling and also as beams for the static calculation. We will now use the possibility of importing the cross-sections in the format of TCL file and import all other necessary cross-sections for this project. After importing the cross-section library and recalculating the project, we will use 3 additional cross-sections for rail spacers, side elements and roadway and railing in order to add them to the already existing main girder cross-section. As a first step, we will define new variables under the submenu variables of the main girder cross-section. 2 variables for the inclination of the roadway and rails with the values of 2.5% and 1 variable for the main girder height. The variable for the main girder height will be assigned to the corresponding parametric line. We will now use the function external boundary for inserting a boundary from another cross-section into the actual cross-section of the main girder. For this, we need to choose the reference point of the external boundary which will be inserted by clicking the intersection point of a boundary and a parametric line. After that, we need to choose by a single click from the project navigation tree the wished cross-section and its boundary, which will be inserted in the existing main girder cross-section. By moving the mouse, we will select the wished orientation of the inserted boundary. We will now use previously defined variables in the main girder cross-section, and in the property window on the right side of your screen, assign them to the internal variables of the external boundary sections. With this step, we made a connection between those two variables, and this behavior we will use later for the definition of the crossfall variation. By using the same function for external boundary, we will insert two additional cross-sections by selecting them in the project navigation tree and choosing the wished boundary and position in the main girder cross-section. Also, we will additionally adjust the variables of external boundary cross-sections and connect them to the main girder variables. In the next step, we will assign structural unit type load to two newly inserted external boundaries. The elements set up in the cross-section as a structural unit type load are used as 3D bodies for geometrical model and as a load for a static calculation. By using the external boundary function, we will import the last external section for the railing, position it in the main girder cross-section and adjust the offset and also the value of the variable. For this external boundary, we will also use the structural unit type load and assign it to the boundary. The position of the structural unit in one cross-section has no relevance for the geometrical and also not for the statical model. When we finish with the definition of the cross-section for the superstructure, we will start with the 3D modeling of the main girder. 3D modeling is done interactively in 3D view. For this, we need to go to the menu Structural Members in the Project Navigation tree, and under the submenu Girders, we will create a new girder with a wished name. After that, we need to select the wished axis in 3D and to select the wished cross-section from the Project Navigation tree. Furthermore, we will enter the start and end station of a girder, which will start at 0 and end at 160 meters, and also we will enter the subdivision type step with a length of 5 meters. By selecting the option Show Material Texture, we can change the type of the preview in 3D window. Table for stationing is automatically generated by software, and we can see the stations where our future piers will be located: 30, 80 and 130 meters. By using the option Insert Stations, we will insert additional necessary stations to the main girder. We will insert stations at the first abutment, 1 meter before and after each pier, and also at the end of the bridge. We need those stations for the future variation definitions, and those stations will allow us to assign the cross-sections to them and also to take over the respective table values. In the stationing table, we can now see all inserted stations. As the 3D model of the superstructure is now ready, we can start defining the variations for the bridge deck. As we mentioned at the beginning, we would like to vary the crossfall of the main girder and also the height. In the project navigation tree, under the menu variations, we will create a new table with the name main girder height. This table we will define by copying the content from the Excel sheet directly. For this, we prepare the Excel sheets in advance by defining the 3 columns, one for the station, one for the values of the cross-section, and the third one for the type of the transition curve. We just need to simply copy and paste the values from the Excel to Allplan bridge interface, and the wish change will be visible in the table and also graphically. By using the same workflow, we will define another variation table for the main girder crossfall by copying it directly from the Excel sheet. According to this table, we will change the direction of the bridge deck crossfall following the orientation of the axis. We just defined the 2 variation tables for the main girder height and the crossfall. One missing step is assignment of the wished variation table to the corresponding variable of the cross-section. This is done in the table for variation of the main girder by simple drag and drop of the wished variation table to the column of the variable. After the assignment with the drag and drop is done, all the respective table values will be taken over in the variation table of the main girder. It is also possible to use formulas and write them directly into the field of the variation table. We will use this possibility and change the value of the inclination for the rails by multiplying it with -1. After the recalculation is done, we can see the 3D model of the main girder. The change of the main girder height along the bridge axis is visible and is following the variation table. The crossfall change is also visible in the 3D model. The definitions for the superstructure are done. And now we can start with the substructure modeling. As a first step, we will model the cross-section. At the beginning of our webinar, we imported already prepared cross-sections for the substructure. The pier cross-section, together with variables for the pier width, which will be changing along the pier height, and also 2 variables for the gap detailing in Y and Z direction. The pile cap cross-section defined as a very simple rectangular cross-section with the dimensions 8 × 4.8 meters. Also the piles cross-section, which consists of 6 piles with a radius of 0.6 meters. For this, we defined one cross-section with 6 separate structural units type beam. We will add 3 new elements of the substructure to already existing superstructure. For this, we need to make some additional definitions. In the main girder cross-section, we will define new reference point at the bottom of the cross-section for the geometric position of a connection at the main girder cross-section for connecting the piers. We will also change the name of this reference point accordingly. After the recalculation of the geometrical model is done, and after the cross-section of the substructure is prepared, we can start with 3D modeling of the substructure elements. In the Project Navigation tree, under the Pier submenu, we will create a new pier with the name Pier 1. After that, we need to interactively select the reference point on the main girder for the connection to the pier, and also we need to select the wished cross-section for the pier from the Project Navigation tree. After that, we will define the begin station of the pier and also the last station for the pier member. The first pier will go from the station 0 to the station -15, and the step for the elements will be 2.5 meters. We will not exit the function for the interactive pier creation, and we will add additional stations with the same cross-section at -0.5 and -1. Those stations we need for the definition of the variations of the pier. Since the 3D modeling of the substructure elements is done, we can start with the definition of the variation tables for the substructure elements. The variation tables for the pier member have been previously defined. We can clearly see the stationing table for the piers as well as the cross-section table. The only left step is assigning the variation tables to the corresponding columns of the variables for the pier. We will do this by drag and drop. After that, the corresponding values will be assigned to the stations, and after the recalculation, the changes in the geometry of the pier member will be visible in 3D view. We will now use the possibility of copying the Pier 1 in order to create the Pier 3, which is completely the same as Pier 1. For this, we need to interactively in 3D choose the new reference point for the position of the Pier 3, which is located at the 130 meters on the main girder. Even in this phase, when the piers are already created, we can still do some changes in the geometry of the pier members. In this case, we will do that by editing the table for the pier gap in Y direction. We will correct the tables in Y and Z direction as well. And after the recalculation is done, we can see the changes in geometry of both piers in 3D preview. In the next step, we will define the middle pier, Pier 2, between two already defined piers. Pier 2 will be defined interactively by selecting the necessary reference point, and that is at 80 meters of the main girder. This pier will have different sections assigned along its height. As a first section, we will select the pier section, which will go from 0 to -15 meters. The step for the subdivision will be 2.5 meters. The next cross-section we select from the Project Navigation tree is a pile cap. This cross-section will go from the stations -15 to -70.5 with the same step for the elements. The last cross-section of this pier member is a cross-section piles, which will go from -70.5 to -27.5 meters with a step 2.5 meters. With these definitions, we defined in one step interactively a pier which has a changeable cross-section along its height. You can see the stationing table for this pier and also the cross-sections table. Since we want to have the same variations of the cross-section as for the Pier 1 and Pier 3, we need to insert the missing stations to the Pier 2 as well, and this will be at -0.5 meters and -1 meter. After that, we will be able to drag and drop already defined variation tables to the corresponding columns of the variables for the Pier 3. After the recalculation, it will be visible in 3D model that the variations are applied to the section of the Pier 3 as well. When we finished with the definition of the 3D model with superstructure and substructure elements, we will additionally define materials. Materials can be defined manually in Allplan Bridge, or they can be imported from the library of materials from Beam+. We will create a new standard, and then we will use the option Import Beam+ Materials. We can import different materials from the library of Beam+. For this project, we will use the Eurocode standard and import concrete material C3545 and C4050. Material characteristics from Beam+ and from Allplan Bridge are available for preview in this window. Material characteristics can be seen on the right side of the window. We will also import steel material S355, pre-stressing steel and reinforcing steel, which we will use further in this project. After the wished materials are taken over to the project, they will be all imported into the project by a single click. After all wished materials are imported, they are available for the preview under the Analysis materials in the Project Navigation tree. The user has the full freedom to edit any of the characteristics. In the next step, we will assign the materials to the elements of the structural members. We will first assign materials to the elements of the main girder. To the structural unit 1, defined as a beam, we will assign a concrete C4050 by using the right mouse click in the wished field. To the structural units 2 and 3, by drag and dropping the materials from the Project Navigation tree, we will assign the concrete C3545. For the structural unit 1, we will use the right mouse click on the first field and apply material to all subsequent stations. We will also use drag and drop option and assign a steel S355 to the structural unit 4. By using the same workflow, we will assign material C3545 to the pier structural members. For this, we will use the drag and drop option or the right mouse click in order to assign materials to the wish elements. After the material assignment is done, we will recalculate geometrical model. All defined materials are used in geometrical model only for rendering and the 3D preview of the bridge model. In the later phases of the project, we will also use assigned materials for the analytical model. When the superstructure and substructure modeling is done, we can start with the modeling of tendon geometry. In Allplan Bridge, any tendon geometry can be defined. In general, there are 4 different approaches of tendon modeling, and the user can choose the most convenient depending on the bridge and tendon geometry. In this webinar, we will define the tendon geometry by varying the tendon grid points. The geometry of a tendon along a structural member is determined by a user-defined series of constraint points. Between these constraint points, the calculation of the tendon geometry in Allplan Bridge is performed as cubic Hermite splines. We will return to the main girder cross-section and define a point grid for positioning grid points within the cross-section. Those points will then be used as a reference for the definition of the tendons. The origin of the point grid will be positioned in the intersection point of two parametric lines. After positioning the point grid, the user has the freedom to edit the properties on the right side of the screen in the property grid. You are able to edit the number of points and also distances in the properties window. We will define the number of points in U and V direction, and also we will edit the offsets and spacing between the points. We will define 6 grid points with a horizontal distance of 0.6 meters and vertical distance of 0.25 meters. It is possible to vary the offset and spacings between the grid points by using variables. Therefore, we will define a new variable in the main girder cross-section of the type length with the name tendons. We will assign the defined variable to the offset in the V direction of the point grid. Since the cross-section is drawn parametrically, the point grid will follow all the changes of the main girder height along the bridge axis. After the point grid is defined, we will start with the definition of the variation table for the point grid. Under the Variations menu, we will create a new table with the name Main Girder Tendons. We will import the table using the same workflow as previously and copy the complete table directly from the Excel sheet. The variation of the point grid is shown graphically on the screen. In the next step, we will drag and drop the variation table and assign it to the corresponding column of the variable. After the recalculation, the variation of the property grid points is visible in the 3D model. Under the geometry tendons, we will start with the definition of the tendon geometry. We will define 4 phases of tendons which will follow the construction sequence. In each phase, we will define 3 tendons. With the right mouse click on the empty area, we will create the first group of tendons with the name Phase 1. Under the Phase 1, we will create a new tendon, Tendon 1. The central working area is divided into the 3 separated windows. Those windows together represent the workflow for interactive definition of the tendon geometry. To define the geometry of the Tendon 1, we will use the function Insert Tendon Point between 2 stations. For this, we need to click the first station as the start point of the tendon series, the second station as the end point of the tendon point series, and also the respective point in the cross-section window in order to define the position of the tendon at these stations. After this, the table with the tendon points is automatically created, and the tendon is visible in 3D view. The upper window is divided into the 3 different windows: 3D model, plan, and developed view, available for the user's definition and the preview of the tendons. Using the right mouse click on the Tendon 1 and using the function Multiple Copy and Move, we will copy Tendon 1 and create Tendon 2 and Tendon 3 of the Phase 1. For this, we need to select the starting station of the new tendon in 3D view, and also using the 2D window, we will select the new point in the cross-section. We will repeat the same workflow in order to create the Tendon 3. With this, we created all 3 tendons of the Phase 1. Using the same workflow, we will create the geometry of the Phase 2 by creating first the Tendon 1, using the same function for inserting the tendon between 2 stations, And after that, we will copy tendon 1 with the function multiple copy and move and create the tendon 2 and tendon 3 geometry. Using the same workflow, we will also define a tendon of the phases 3 and 4. And with that, we will have the complete tendon geometry defined. After the recalculation, the tendons are visible in the 3D model of the bridge. Since the complete 3D model with the tendon geometry is ready, we will continue with the construction sequence definition. In this stage of the project, when we define only geometrical model, we will define 6 different construction phases in order to simulate the construction sequence of the bridge. Under the tabs Analysis Constructions, we will create the new construction, using the right mouse click on the empty area. Under the new construction, we will create one new phase, phase 1. After the new phase is created, the working area has changed and the new windows are opened for the interactive definition of the construction sequence. In the action bar, the task construction is opened and it includes all tools for defining and simulating the constructions and their phases. In the first construction phase, we would like to activate the elements of the substructure, piles and pile cap of the Pier 2. Under the construction task area, we can find many different tasks, also available in a drop-down list. In order to activate the elements of the piles and piers, we will choose the task Concrete, which will simulate the activation of the elements. Each task can be related to a particular structural member or its part, and this is assigned by defining the assemblies. The assembly can be defined interactively in 3D by selecting the wish structural members or their parts. Selection options are available for the user, together with the view options and the filters in order to make the selection in 3D window much more user-friendly. After the assembly is created, the activated elements are available in the list on the left side. For each task, the additional properties can be defined on the right side of the screen. The beginning of a task can be defined as a start date or start day, and the end of the task can be defined as the end date. It is also possible to define the duration of each task. For this task, we will define the start day 1 and the duration of 7 days. Each task is available on the right side in the graphical preview and also in the list on the left side. The defined tasks are shown graphically in the Gantt chart, and the user can also edit them directly there. We will use additional options available on the right mouse click in the context menu and copy the phase 1 into the phase 2. The task Concrete was copied together with the phase. The only thing which is left is definition of the assembly for the task Concrete. For this, we will interactively select 3 defined piers, Pier 1, Pier 2 and Pier 3. We will also change the start day of the task Concrete in the phase 2 to 14, and duration of the task will be 7 days. It is possible to select the wish date in the Gantt chart and also to change the zoom of the timeline in order to see all defined tasks at once. We will use the same approach and copy the phase 2 in order to create the phase 3. In the phase 3, we will activate the first part of the main girder, and we will also stress the tendons of the first phase. For the task Concrete, we will create the assembly by selecting interactively the elements of the main girder structural member from 0 to 35 meters. In the property windows of the task Concrete in the phase 3, we will adjust the start day and the duration of the task. From the construction task area, we will choose the task Tension in order to stress the tendons of the phase 1. For this task, we will create the assembly by selecting interactively in 3D the tendons of the first phase. Please use the view options and the filters for a much easier selection of the tendons. When we finish with the definition of the start dates and the duration for each task, we will continue to define the phase 4. The phase 4 will also consist of the task concrete and the task tension for activating the elements of the main girder and for stressing the tendons of the phase 4. We will use the same interactive selection in order to activate the elements of the main girder and the tendons of the phase 4. After adjusting necessary start dates and duration of the tasks, we will continue with the definition of the last two phases. After the complete construction schedule is defined, all the tasks are available graphically in the Gantt chart. It is also possible to play an animation of the defined phases and constructions on the basis of the geometrical model in the 3D window at the bottom. All the tasks will be played with the start date and the duration which was defined previously. It is also possible to adjust the days per second as the speed of the animation. With this we finished with the construction sequence definition, and we can continue with the definition of the smart placements in order to parametrically define the position of some elements in Allplan bridge, which will be then connected to the library elements in Allplan engineering. In this specific project, we will parametrically position the vertical elements of the railing in Allplan bridge and connect them to the library elements previously defined in Allplan engineering. Those elements are defined in Allplan engineering as smart symbols, and once defined, they can be used in all future projects. In order to properly define smart placements in Allplan bridge, we will need to add additional definition in the main girder cross-section. First, we will add the missing parametric point on the left and on the right side of the main girder cross-section in the level of the railing. In those defined parametric points, we will define the reference points, one on the left and one on the right side. Important is that those reference points have the same name as the library elements from the Allplan engineering. In the Properties window on the right side of the screen, we will activate additional options for both reference points, as Placement option and option Y Global for positioning the elements vertically in the Y global direction. In our next step, we will define the new dimensionless variable in the main girder cross-section. This variable we will assign to both reference points. With this additional step, we connected the position of the smart placements in 2D with a position in the longitudinal direction, which we will define in the further steps. After recalculating the project, we will go to the main girder variation table, where we can define the position of the smart placements in the longitudinal direction. By defining the ones and zeros in the corresponding column of the dimensionless variable, we can decide in which station will the smart placement be defined and in which not. In this example, we will define ones in all the stations, and then we will additionally define values 0 before and after the piers, and also at the beginning and at the end of the bridge. It is also possible to define the variation for the positioning of the smart placements and assign this table by drag and dropping to the corresponding variable column. After the recalculation is done, we can see the smart placements positioned in longitudinal direction and marked as the black arrows. With this final step, our model is ready to be transferred into Allplan engineering for the further detailing and drawing production. Under the bridge construction role and Allplan bridge task area, we will use the function import Allplan bridge data in order to transfer the bridge model from Allplan bridge to Allplan engineering. The user is free to define the workspace and the location of the project
and also to select between different options for importing the bridge model. When the bridge model is transferred to Allplan Engineering, we can see the library elements positioned at the positions of the smart placements defined in Allplan Bridge. Those positions are parametric, which means that they will follow the changes in the geometry defined in Allplan Bridge. If we now go to the Objects tab, we can see the list of the different objects which our bridge model consists of. This list of the objects is directly dependent on the input options which user chose at the beginning of the transfer. We can also play with the different visibility and the preview options available in Allplan Engineering. With this final geometrical model defined in Allplan Bridge and transferred to Allplan Engineering, we would like to finish the first webinar from our series. Thank you for your attention and see you on the next webinar, when we will deal with the structural analysis in Allplan Bridge.